All right, hey, the recording is for September 5th. We're in ESM 105. You've only missed review stuff. It was in the last video. Watch the last video. Okay, and we're back. P-values. We talked about them. Everyone, any questions about this so far? Awesome. Okay, we're just going to keep moving forward. Independent variables, right? The independent variable is what the researcher manipulates, okay? Or if you're looking at a natural or observational experiment, it's the thing that you're saying had an effect in nature. Let's say that sometimes in a natural experiment, you score and there's a big ecological event, like there is a flood or there is a volcanic eruption. And that's sort of a natural manipulation of the environment. You didn't have to do anything. We call that a natural experiment, okay? So we've got natural experiments, observational experiments, it's all this different stuff. But the thing that you measure that you say is going to affect something else is the independent variable. The dependent variable is the thing that you say is going to change in response to the changes in the independent variable. Changing latitudes adjusts the ratios of C3 versus C4 photosynthesis in plants. All right, I'm saying changing the latitude, the independent variable, will affect the ratio of C3 to C4 photosynthesis in plants. Cool? We'll talk about that again later, so it'll be fun. Here's the example. Are there any questions about identifying this? This is your first big step. And remember, the independent variable's always on the x-axis, and the dependent variable always goes on the y-axis when you are graphing data. Cool? Quantitative versus qualitative data. Quantitative data is easier to use in statistical analysis. So I put here that quantitative data is the gold standard, right? Quantitative data is something that has a number associated with it, okay? Now, the definitions of quantitative data have become very loose over time. It used to be that more quantitative data was something that I would say, what is the height of this thermos? And all of you here could come up and measure the height of this thermos, and assuming that you were doing it correctly and not like measuring it like this, you would all get the same measurement. And that's like quantitative, objective, true quantitative data. But now we can say, well, rank on a scale of 1 to 5, with 5 being the coolest. How cool is John's thermos? I give it a 5. And then you all go, John's a freaking nerd very clearly, and he bought the worst Stanley. It's the bad one, and it's a 1, all right? That's quantitative data still. But you need to be able to say, like, hey, what's the strength of this data? Sometimes you have to rely on survey results. We still count it as quantitative data in our analysis, but it's good to have true quantitative data where you are objectively measuring something. All right? Cool? Did I talk to you about turf grass science yet? No, not, yes, a little bit? No, I can't, all my classes, they overlap. That was my job when I was in my PhD program. I worked with turf grass, all right, and tried to reduce water requirements. Okay, that was my goal. That was my whole mission by using biochar products. Getting the turf grass industry to adopt biochar products. My goal, my hope was, we'll get a bunch of carbon sequestered in the soil. The turf grass people were never really that into it, but maybe they'll change their mind someday. All right. The point is, when you're measuring turf grass quality, there's 2 ways to do it. You can do it qualitatively, where you say, oh, that looks good, that looks bad, that looks like it's improved, it looks like it's not, like it's gotten worse. Okay, these are qualities. Or you can quantitatively measure turf grass quality by, say, taking a picture and then using digital image analysis to determine the hue, saturation, and brightness of the image and run that through an equation to get a dark green color index. And that gives us a true quantitative measure of turf grass quality. Are you sort of seeing the difference here? Now, qualitative and quantitative data need to be dealt with differently. But for statistical tests and the ones that you'll become comfortable with in your undergraduate, assuming you're not becoming a statistician, okay, quantitative data is going to be the most straightforward. So it's good to try to find a way to take any qualitative data you encounter, like good versus bad or improved versus not improved, and convert it into qualitative data, like rate on a scale of 1 to 5. Now you've got numbers, 1 through 5. You can take the average, get the variance, do the statistics. A lot of stuff coming at you. How do we feel about this? Awesome. Yes, question, please.
So, like, saying, like, out of one, so saying, like, oh, I like this movie on a scale of 1 to 10, that's quantitative data?
It is still quantitative data, yeah, for the purposes of all of choosing statistical tests and doing these statistics.
But it's not really like a measurable, I mean, I guess it's kind of, usually you do measure it.
Yeah.
It's like, and then usually you're supposed to, like, turn that into qualitative data? Or is it...
No, you want to keep it quantitative data for the statistical tests to work. Survey results are a bone of contention, or a point of contention for me, and, you know, it's a standard issue in ecology and in natural resource conservation, especially when you're trying to get, like, do people approve of the changes that you've made to this site or something like that. But a scale of, like, ratings on a scale of 1 to 10, it still gives you numbers, okay? So it's still technically quantitative data, and you still analyze it that way. But it's really good that you catch it. I'll get to you, I promise. But it's really good that you catch that, okay? Because there's also this thing called ordinal data, where if you're rating a movie on a scale of 1 to 10, the difference from 3 to 4 is not the same as the difference from 9 to 10, right? I'll see a good movie and be like, it's like, you know, it's like an 8 or a 9, but it has to be a great, like, perfect movie to be a 10, right? So with ordinal data, which should be analyzed differently and essentially never is, the difference between each value is not the same. The difference from 3 to 4 is not the same as the difference from 9 to 10. So when you're dealing with a survey, you're usually dealing with ordinal quantitative data. But nobody usually incorporates that. You just pretend that the numbers are all, that 1 to 2 is the same as 5 to 6.
I can see how that's, like, tricky.
It is tricky, but it's good to recognize still. Yeah, awesome. We good? Cool, yes, please. Quantitative data should always be represented by a numerical value, yes.
And qualitative data is usually represented by, like, adjectives.
Yeah, exactly. Like the classic example in every Bio 105 textbook is Jane Goodall, and you go like, oh, that chimp was angry, and that chimp was sad, you know? And so those are descriptions where you can't be, like, quantifying, but you could theoretically, nowadays you take a picture and you go like, or a video, and you go, this chimp spent 10% of its time doing this face, and we've associated that face with a display of aggression, and now it's quantitative. You know what I mean? That's basically, that's exactly it. And then some qualitative data is like, thanks for visiting our park. Please provide your thoughts. And that's hard to analyze, because now you gotta be like, classifying each one as positive or negative, and saying 10% of people had a negative feeling. But what have you done there? You've made it into quantitative data. That's almost always what people end up doing. Make it quantitative and then analyze it. That's my advice to you as a budding statistician. I'm so excited to talk about statistics with all of you. I don't know. It just puts me in such a good mood. I'm sorry it's so dry. I really do apologize. It's just such important stuff. And if you get it here, you won't have to deal with struggling as much as when you have to learn it again in the future. I promise, it's worthwhile. Okay, let's keep on moving forward. Now, we've got some data. We've determined if it's qualitative or if it's quantitative. It can be either qualitative or quantitative, and then we can break it into different categories, or we can have a number that can fall anywhere within a range. I'll explain in more detail. It's better with examples, okay? The height of this thermos, all right? Its height could theoretically fall anywhere within a given range of values, okay? If I took the average, if I wanted to measure the average height of water bottles in this class and compare the height of water bottles in this class to the height of water bottles in the class next door, I have a hypothesis that, hey, we're going to have, they have bigger water bottles over there because they're thirstier. Or you have bigger water bottles on floor 5 than on floor 3 because you get thirstier. All right, it's a weird hypothesis, but it's fine. What do? Well, we measure the water bottle height of everybody in the room or everybody on the floor, okay? And each water bottle could fall anywhere within a range of values. So it's continuous data. It can fall anywhere within a range, okay? Now, I could also set up categories and say any water bottles that fall between 10 or under 20 centimeters high, these water bottles are classified as small. Anything that falls between 20 and 30 centimeters is classified as medium. Anything that is 30 centimeters or greater is classified as a large water bottle. Then I go around the room and I say, oh, there were 3 smalls, 10 mediums, and 2 large water bottles. So that's categorical data. But I still measured both with a ruler. It's just about how you handle the data usually. Sometimes data falls into categories, clearly, like north-facing and south-facing aspect. Sometimes you set up the categories like low, middle, and high elevation. Sometimes you measure things continuously like elevation. Do you kind of understand what I'm trying to get at? I was hoping that the example might help. Okay. So some examples, right? High, medium, low. These are categorical data. North, south, improved, unchanged, worsened. You still get counts for each one of those categories, so it can still be quantitative. Then we've got continuous data right there. Depth, density, concentration of lead. The value could fall anywhere within a range. Cool? So now we've become comfortable with the idea of quantitative and qualitative data. I've hopefully done a decent job of convincing you. Just make your data quantitative for the purpose of a statistical test. Find a way to make it quantitative. It'll make your life easier. Now we've got independent and dependent variables. You're comfortable with those, right? You know that you're saying the dependent variable depends on the changes in the independent variable. And finally, we've added that piece of categorical versus continuous variables. Do we count things as categories, or do we measure something directly that can fall within a range? And that's everything you need to know to select the correct statistical test. All right? Besides, is your data normally distributed or not? But I'll throw that on at the very end because it's an annoying additional piece. P-values we've talked about. Do we have questions about p-values though? I saw a video right before I started teaching of somebody walking around a professional ecology conference, and they were interviewing people who were giving presentations, and they would ask them like 2 questions, and the third question would be, can you explain a p-value to me? And they just made this big master cut of nobody knowing what a p-value was. And it was discouraging as somebody who was becoming more and more of an ecologist. So now, in all of my classes, I try to avoid that situation happening. You should know what a p-value is. All right? Yes, please. Yeah. So it's straight up probability. So yeah, yep. This is the probability of rejecting your null hypothesis if it's the probability of receiving the results that you did if the null hypothesis is true, right? Awesome. You want it to be a low number. Well, you don't want it to be a low number. That's such a silly thing for me to say. You want to collect your data honestly and get the results that are the results of your experiment. Not disproving your null hypothesis does not make the experiment bad or unpublishable. It makes it more difficult to publish. I'll tell you from experience, because I've had studies that went that way. But, you just go to a lower impact factor journal. It does matter. Negative results are still results, right? We say that in academia all the time, and then it's not practiced when you get into actual publication, unfortunately. Yes?
Kind of off topic.
That's okay.
Any reason why journals would not want to publish studies with negative results?
It's not, my very cynical perspective on it is that it's not as exciting. The titles are usually very bland, and bless you. And that's about it. You know, journals want to be publishing things that change our current understanding. And when you don't disprove your null hypothesis, you're kind of just saying, there's no interaction. It's kind of exactly what we expected. Here's nothing new. You know, when you said I had an article that was all about biochar does not impact turfgrass establishment rates. And that's a huge deal for turfgrass managers because anything that affects the rate of establishment of turfgrass seriously impacts their business, right? But people weren't very excited about publishing it. And I got that feedback a lot of like, so there was no impact of the biochar amendment. And I'm like, yes, but that's what we wanted to show. We never thought it would increase establishment rates. We didn't want it to change the rates from the control. What is wrong with this world? And you know, so I'm not bitter anymore though. I don't care at all. Yeah. So why would they not publish negative results? They're not as exciting. Of course, sometimes journals have biases too, but I am not claiming any bias against biochar in these journals. They wanted to publish biochar work, but they wanted something exciting, which is weird because you're not going to make these journals exciting. They're never exciting. Even when you put a really thrilling picture on the cover of Nature and it's like, a big meteor's coming down and we're rethinking how these two species of dinosaurs are related. I'm not gonna, I mean, you're gonna pick that up? I don't know. I got my phone right in my pocket. It's way more fun. Yeah, they should. They really should. Okay. P-values all laid out for you here, like what actually goes on. It's super dry. What a statistical test does is it takes your sample, it takes some averages, it takes some variance values, which is just how much difference there is between similar data points. So like similar independent variable values. How different are the dependent variable values? So you get all this variance data, you get these average values, an equation happens and it says, hey, if all these values were the same, then this test statistic value should be blank. And then it actually calculates the test statistic value from your data. And if that test statistic value is higher, then you invalidate your null hypothesis. And all of the statistical tests just do that. All right? How do they calculate the test statistic? Who cares? Right? I mean, statisticians care, but it doesn't really matter. From our perspective, it's always a measure of averages and variances, or with a regression, it has more to do with you fit a line and how good does the data fit the line, or does the line have a slope to it? I'll show you. But this is it, you know? Let's look at the main statistical tests that you'll encounter. Those are the t-tests, ANOVA, and the linear regression. If you're sticking with ecology or conservation, right, you're probably going to eventually see nonlinear regressions that are looking at, say, growth rates of populations. Populations don't grow in a straight line. They grow like exponentially and then they level off, all right? But it's a similar principle at play here. So check this table out. There are a lot of tables like this. I also have a flow chart here that I like a lot, even though there's a typo in it, which is frustrating, but I like this flow chart a lot. You've got explanatory variable, that's the independent variable. You've got the response variable, that's the dependent variable. The variable is going to respond to the explanatory variable. The explanatory variable explains the response variable. So it is independent on the top, dependent on the bottom, okay, or the side. And look, if the explanatory variable is categorical and the response variable is numerical, so it's floor 3 versus floor 5, those are two categories. Water bottles on floor 3 versus water bottles on floor 5, okay? Categorical independent variable. A numerical or continuous dependent variable of water bottle height. Well then, you just use a t-test because there are two categories for your independent variable. If I was comparing floor 1 to floor 2 to floor 3 to floor 4, then in that case, I would use an ANOVA. So if there's only 2 categories of independent variable, all right, then I use a t-test. Just remember T for 2, even though that's not where the name comes from, okay? And then if there are more categories than that, I use an ANOVA. And check this out. There's a note here about normally distributed versus non-normally distributed data. In practice, what this means is before you start doing your statistical tests, you hit a button to see if the data is normally distributed. And if the data is not normally distributed, then instead of running the T or the ANOVA, you run a Mann-Whitney or a Wilcoxon rank sum test. It's a different button, okay? But most of the time, you'll be encountering t-tests and ANOVAs, all right, or linear regressions. So with a linear regression, what we've got is a continuous independent variable where the value can fall anywhere within a range, elevation, latitude, etc. And then a continuous dependent variable where the value can fall anywhere within a range. Bless you. It means that we're not going to have a bunch of replicates within each category. The benefit of having categorical data is if I'm comparing floor 1 to floor 2 to floor 3 to floor 4, right? I've got 40 water bottles on floor 1 and 20 water bottles on floor 2, right? So I've got all these different replicates. It's going to make it easy for me to get an average and a variance and jam those through an equation and get a p-value. When you're comparing a continuous thing like elevation to a continuous thing like plant height, all right, you don't get a lot of replicates at each. You're going along an elevation gradient. You're running a transect line, and you're taking measurements, okay, every time you encounter a plant. See, so that's not going to give you an even number of replicates or really necessarily a lot of replicates. But what you're saying is that there is a correlation between your independent and dependent variable. What you're saying is, as I change my independent variable, then on average, my dependent variable should either increase or decrease. All right? So to determine that, all you do is you fit a line and you see if that line has a slope to it. If the line has no slope to it, then there's no correlation. There's no interaction. If the line has a positive slope, then an increase to independent decreases dependent. If the line has a negative slope, then an increase to independent decreases dependent. Not so bad. Here is the other sort of flow chart here. I like this one, except that whoever made it put just variable here, which is annoying. That should say independent variable. And then it's like, why do they have these broken up? So the flow chart's not perfect, but it does lay out all of the different types of analysis that you're likely to see. And I like that it just says regression instead of linear. It's like you use some type of regression here. And here's my actual goal in a lot of the explanations I give you is if you're going to continue, my assumption's always you're going to continue in academia or research or something associated with this field. It's the only way to teach a class, right? My assumption being that I want you to be able to go to so whoever's training you or a supervisor or whoever, and at least have the basic reasoning part done so that you can start communicating on a more advanced level. They're going to have their own way that they do things in the lab. If it's an agency, they're going to have their own tests that they use, their own statistical software they like to use. But it's really nice if you can walk in the door and be like, hey, so we collected all this data. I went ahead and ran a few tests in Excel, and here they are. You know, it looks like there's a correlation between these two variables. And they'll go, wow, that's a great initiative. That's incredible. Awesome. We need to look into that more. Now, technically, we should be using a logistic regression, I think, here. And you can be like, oh, I never really got comfortable with those. I'm like, no problem. Train you up. It's way better than going, hey, listen, I went out there and I got all this data. Good to see you. Bye. You know? So that's my goal. Is to get you to the point where you can start on a good foot. You know? Anyway. Metric dependent variable. This means it's a number that you can measure, right? So we've got the continuous dependent variable in all of these examples actually here. Categorical dependent variables are pretty rare, especially if you've done the legwork to turn your data into a quantitative value. All right? Sometimes you got to compare a category to a category, but that's odd. Anyways, t-tests, ANOVAs, and COVAs. This is the slide that I think I'm the most proud of for driving all this home. All right? I've got an example of the three main statistical tests. If there's one other test that you are likely to see, it's you might see a chi-square analysis. You might see one, but it's a very specific situation. And I'll tell you from speaking with actual, like, real deal ecologists, I've asked them in private and been like, hey, so when do you use the chi-square test? Because I got this data set here and I'm thinking it could be either. And they're like, just don't run the chi-square. You know, run it as something else if you possibly can. It's really interesting. So, I don't know. Take that for what it's worth. That's the truth. You'll see one of them. But here, get comfortable with these three, and you'll be happy you did. Check it out. T-test, categorical independent variable with two categories, before and after. Before and after what? Does not matter for the purposes of this example. Dependent variable, okay? It's something that you measure that is continuous. Values fall between about, like, let's say 62 and 85, or 62 and 95. It's fine, right? You get your two categories. You have all these different replicates. You take averages. You calculate the variances and the standard deviations or the standard errors, and you make these box and whisker plots, okay? Now, the box and whisker plot is great for visualizing the data, but the p-value spit out by the t-test will let you know if there's actually a difference between the two categories. Your null hypothesis is always that the independent variable has no impact on the dependent variable. Cool. Over here, we've got the ANOVA. And in the ANOVA test, it's just like the t-test, but there's more than two independent variable categories. Fair enough? Awesome. I've learned that students are more and more comfortable with box and whisker plots than with bar graphs. And I think it's because Google Sheets by default does box and whisker plots, and Excel by default does more like bar graphs. But hey, I'll change with the times. I am nothing if not flexible and hip. See this move? It's my hip move. It does make it true. Yeah, absolutely. I said it this morning. I woke up, I was like, I'm hip. All right, let's look at these regressions, okay? You've got a continuous independent variable and a continuous dependent variable. This is a linear regression because a straight line has been fitted to it, all right? And the test actually just says, it estimates the line and gives you like a variance measurement of how much that line could teeter and totter. And it's like, is the slope of the line positive, significantly positive or significantly negative or significantly different than 0? Any slope of the line indicates a correlation between the two, and that's what the regression tells you, right? If you get a p-value less than 0.05, changes in the independent variable change the dependent variable. Cool? Two important things that get spit out by a regression. One, the line equation. The line equation, which will get spit out by this, okay, is a model, okay? What it tells you is I can plug in any value of height here, and I could convert it into a weight prediction. So I could predict weight with any value of height that I'm given. Or, technically, if I know the weight of one of these things, let's say they're giraffes, okay, then I could predict the giraffe's height using this simple linear equation. Sometimes the line is more complicated and curvy, it's like a polynomial equation, but the effect's always the same. You just get an equation that you can use to predict one thing with another thing. That's great, but there's an additional second value, okay, which effectively tells us how good is that model. How well does the data fit that line, okay? And that is right here, the R-squared value. So you see, there's the line, okay, equation for this line. Here's the r squared value. The r squared value is mathematically determined by measuring the distance that from each one of these points to the line, okay? If the points fall directly on the line, it's a very strong model. If the points are very scattered around the line, then it's a weaker model. This r squared value is 49.7%, all right? You can get this all spit out by Excel if you're using Excel, which means technically that 49.7% of the variability in weight is explained by variability in height. A higher value is better. A low value indicates to you that there's something else at play. There's some other independent variable at play here. Okay? And there's so much to learn about how do I incorporate multiple independent variables at once? But we just want to get you to the point, this is ESM 105. I just want to get you to the point where you can select one of these. It gets you at least in the right ballpark. And then you'll be like, well, I need to run a regression, but with 2 independent variables. And now you're off to the races, because you actually know what you need, you know what to search for, you know where to go in the textbook or online. Okay, that was my all of statistics PowerPoint. I hope you enjoyed it. Let's move on. Models. A couple of people in the discussion section mentioned how they really liked this models section. I like it too. It's pretty cool. Modeling's a big piece of ecology. And with the week 1 through 2 PowerPoint, part of it is basic ecology. So, generating models. Models are usually mathematical representations of trends or correlations that we see. All right. So for example, the linear regression spit out a model that correlated height of giraffes to weight of giraffes. All right. And let's just make predictions. More complicated models let us make predictions of, say, global ocean patterns, wind patterns, precipitation patterns, changes to plant communities over time, frequency of fires in a given area, given other information about, say, frequency of lightning strikes, relative humidity, etc. The goal is, as an ecologist, is to make models that make accurate predictions without overwhelming them with variables, okay? Have as few variables in the model while still maintaining predictive power, okay? Cool. That's basically what I said there. Models, you take complex systems and predict. Yeah. This includes here model organisms, which is really interesting. I'll keep it super brief. Model organisms are species like Drosophila or Arabidopsis or tobacco. These are all species of plants or animals, or E. coli is a model organism, all right, that have been very, very well studied. And there's been a bunch of mutants of them generated, and there are lines maintained where there's mutants that, say, have an issue with wing development in Drosophila. They don't have any wings, okay? So you can study what led to that lack of wings. Or maybe you try to do a genetic engineering experiment where you get them to regrow those wings, and now you understand the genes responsible for wing growth. It's a super oversimplified example. And then, those model organisms get marketed to consumers, and they'll just be like, here, buy this glowing fish, and it's like, that was initially used in research in order to test if you were getting these genes into organisms. But now you could buy a glowfish, you can get wingless flies, all right, to feed your animals if you don't want the flies to get out, all sorts of stuff. Anyways, models. Let's stick with the simplified. It's on theme with talking about models to try to keep it simple. Models are flawed. You don't have to memorize this. I'm so sorry if it's overwhelming at first, but here's the idea. This is one of the most commonly taught models, mathematical models in ecology courses, in ecology courses. It's the Lotka-Volterra predator-prey model. All right? Oh no, this is the competition model. My bad. So what this model lets us do, okay, you take two species that are in proximity to one another, and you can predict each species' population level based on how much they affect the other species, how much of a competitive detriment they cause to the other species. So it's, it's a really useful model. But you have to use the simplified variable of the competition coefficient, all right? Which basically tells you how much impact does species 2 have on species 1 via competition, all right? How do you determine that? With a bunch of observations. What you're trying to do is simplify this down to the point where you have as few variables as possible, so that then you can make predictions of how populations will change over time. So Lotka-Volterra competition model. Lotka-Volterra did a bunch of stuff. The two of them did a bunch of stuff with modeling populations of animals. Really fascinating story. Vito Volterra, interesting character. Okay. Check this out. These models will usually predict something very clean because there's no inclusion for external factors. There's no addition of all the other species that these two species are interacting with, or environmental stochasticity where something random happens, all right? Or, like, say, the other things that these animals are consuming, right? So we've got here this classic example comparing hare and lynx populations, all right? In Canada, there was a bunch of fur trapping going on for these lynxes, and so people were keeping track of the populations of lynxes and the populations of their primary food source, hares, okay? Now, they can model how these populations should interact. And it's basically this. Prey populations peak, predator populations have a little bit of a lag behind them. So as there are more rabbits, there can be more wolves, all right? At a certain point, there are so many wolves that the rabbit population begins to decline. And then, with a slight lag behind it, the predator population begins to decline because their food source is no longer there, all right? If you plug most combinations of population sizes and predator-prey interactions or competition coefficients into a Lotka-Volterra model, you get two smooth curves like this. But then in reality, you get something more like this. And you can see that there's still a similarity to the curve. Like, look right here. Hares peak, lynxes peak, boom. Okay? There's a lag behind them. These ones are more synced up. So the model is an oversimplification, and sometimes it can let us make good predictions. It can be really useful from a very, let's say, pragmatic perspective of the people trapping for furs. It's like, oh, well, we know that the hare population is about here, so the lynx population is about to plummet. We really shouldn't be trapping right now. Okay? It's things like that, The model lets us make predictions. That's when you know you've got a good ecological model. I just need to hit the escape key, and I always forget to do it after I'm zoomed in. Let's correct the behavior. I zoom in, I hit escape. There we go. Now my body knows to do it that way. All right, systems, okay? Systems are important as a concept. Hey, okay. Systems are important. Basically what you do is you constrain something, right? So you can understand the internal mechanisms of it. So a cell is a system, a mitochondrion is a system, all right? An organism can be looked at as a system, where it's got these inputs of food and water, and it's got these outputs of wastes and gases that it breathes out, all right? And an ecological system can be studied, a certain biome could be studied, a certain habitat could be studied, a certain ecosystem, a certain artificially constrained area, a certain national park, a certain building. Understanding things as systems, all right, lets us focus in and simplify the overcomplicated world around us, right? Is it overcomplicated or is it just the right amount of complicated? I don't know. But you see the theme here between both models and systems? It lets us simplify, okay? So we can study a specific thing. Awesome. So here we go with some basic terminology of systems. All right. Yeah. There'll be a variable that we are tracking throughout a system. A variable just being something we can measure. So like we're tracking carbon throughout a system, or we're tracking energy through a system. And that thing that we are tracking changes forms as it moves through the system. Carbon changes forms as it moves through your body, all right? Energy changes forms as it moves through your body. Energy changes forms as it enters and then moves through a food web, all right? So these are state variables, resources that move from different states. So we've got this external energy input here, which generates these high energy organic molecules consumed by an herbivore, which then builds its own high energy organic molecules inside of it, and then it gets eaten, and then the energy changes forms again into this animal here, which then decomposes, and it's a beautiful cycle. It's a circle of life. All right. Systems. All right. They're not that tricky, I promise, especially after talking about all that statistics stuff. Systems will hopefully be a nicer concept for you. A system can be open, a system can be closed. An open system has an external source of these state variables. Something outside is providing stuff, all right? So the Earth is an open system because it receives an external source of energy from the sun. In a closed system, there's no external, there's no exchange of energy or matter outside of that system, okay? So it's hard to come up with truly stable closed systems because with closed systems, they just run down. A closed system runs down to a stable state, energy can't change forms, and everything dies, all right? So an open system, things flow through the system, okay, into and out of it, and the things that flow through are called throughput. All right? Not too bad. Not too bad. Positive and negative feedback loops. So feedback loops are a huge and important concept when we're talking about systems, okay? We simplify a living organism into a system. We simplify a community into a system. There are some processes that lead to... There are some processes that self-perpetuate, okay? And those are driven by positive feedback loops. And there are some processes that self-inhibit. Those are driven by negative feedback loops. And I think that's a very good place for us to start on next Monday. We're a tiny bit behind because of the holiday on Monday, but that is all right because the week 3, week 4 PowerPoint is shorter than the week 1, week 2 PowerPoint. So please go ahead and complete the, do participate in the discussion section today, all right? You want to get those points? It's 3 points. Hop on there. And then we're going to run through, oh yeah, this will be great. Food webs and energy through, yeah, state variables, and then the carbon cycle, the nitrogen cycle, yeah. Have a great day, everybody. Have a good one. Of course, enjoy the rest of your Friday. Yeah. Oh yeah, we got fun stuff coming.
I just wanted to let you know I am having a problem that is completely my own.
Okay, well, let me stop this recording.